Okay, so folks, sorry for the late start here. Just creating a lecture actually for the first time about a topic which has come up periodically over the years, having to do with functional abstraction. And I thought it was high time I actually carved out some time in the semester to address this issue. Maybe someone in the back could get the left light switch there, just so it isn't so washed out. I think this projector is unfortunately getting into its senescence. Great, thanks a bunch. So we talked last time about functional abstraction. In fact, the last couple times we touched on it, and then last time dealt with it more squarely. Functional abstraction having to do with taking many particular, what could be many fragmented bits of code that all share a lot of commonalities and putting them into a function. So we can have a single function that does that job, rather than having lots of examples of the same basic code scattered around our code base. We put it in a function, we give it a name, and we have that function there for use by calling at many places. And we talked about two ways that we secure types of abstraction from this. One was this abstraction by parameterization. So the idea here is that we have many particular copies of this piece of code all around, and they differ only in certain details involving, say, the data that's being manipulated, or the number of times a certain operation is being done, or what have you. Or we have hard-coded constants in different places and that are used to multiply something. And we abstract that by creating a function which takes in those values as parameters. Remember that? So we carve it off into a function, and we give that function a nice name, and we give it parameters that allow there to be many different uses of it, even if they differ in the precise way that they're using it, with different values, for example. But we captured that code as a whole in the function. And then we talked about how we can also secure abstraction through specification. And here, the idea was that rather than just having to sort of go through, and every time we create a new version of a function that uses a different algorithm, we have to go through the code base and tell it, hey, point to this function rather than this old one. We provide a contract associated with that function. And the contract promises certain high-level things. It promises what the function does at a high level, but not all the details about how. And what that means is the things that call it shouldn't be counting on how it does its job. And as a result, if we go and we wish to have a better version of the function, faster one that has more clever algorithms in it, one that's more robust under error conditions, we don't have to go throughout the entire code base and say, hey, point to this function instead of this old one. Instead, we just plop that into that function because we haven't changed the contract. All we've changed is the implementation. And the specification only promises certain things, and those should be the things that people are counting on. It's kind of like FedEx. If you got to ship a package, they can change, who happens to drive it to the airport, at what time they leave to account for traffic. They can change what plane it goes out on. If you deliver a package at different times a day, who the carrier is, you don't have to worry about it. From your perspective, all you care about is that the contract associated with FedEx, that they will, if you deliver it by 10 a.m., the package, they'll get it to Ottawa by 5 p.m. That's what you care about. And you let them change their whole mechanism as long as they can ensure that contract. And that was the idea of abstraction by specification. We shouldn't have to have this tight coupling where if we make a change here, we have to make changes all throughout the code base, right? That way lies madness, as King Lear said, although not about abstraction. Okay, so let's, actually it was the fool in King Lear, excuse me, that's what Shakespeare said. Okay, but Shakespeare also was not thinking about functional abstraction, though it would have been worthy of the bard. Okay, so ladies and gentlemen, as I mentioned, a question comes up about this. I hear it maybe every year on average, maybe every few years from a student, and often it's from a really good student. Students really thinking about things, putting things together they've seen in different classes or they've experienced as a software developer. And it has to do with the trade-offs associated with this. The fact that functional abstraction is not all simply chocolatey goodness. It actually has limitations, it has trade-offs, it has upsides and downsides, right? And I've been emphasizing the upsides because in my experience as a software engineer in industry and writing lots and lots of open source systems or systems here in academia, the upsides are very, very compelling. However, it is important to know about the downsides, if only to shield yourself from them, to know how to be savvy about dealing with them so that they don't bite you, to know the little things you have to do to prevent them from becoming a big issue, to keep them small. Okay. So we've talked about functional abstraction and how it works, and we've talked about how it's a key component of it through abstraction by specification is the separation of the implementation from the interface. Right. What is promised from the details of how it's accomplished. That gives us a lot of decoupling. And here are some, real benefits, right? These are not all. These are not exhaustive, but easier modifiability, transparency, easier later reuse, and reduced complexity on the part of someone looking at the code, reasoning about it, trying to debug it, trying to test it. Really testing should be in here, and probably easier peer review should be in here because it's clear what the contract is. Testing, peer review. Even if the specification is not fully written out, which is a best practice in many software development firms, but even if the specification is never written out, at least you have some clarity in the form of comments, perhaps in the form of naming, that gives you a sense of how to better judge it in the context of peer review and testing. So lots of good things here, and I'm not going to go over them. What are some limitations of this? Well, I just put down two, and they're quick to read, so just read them. Well, one of them is, and I think probably a lot of people have been in this position before, there are cases where you come to a code base. Maybe you're taking it over from someone who's leaving the project. Maybe you're taking over from someone who's going to go on mat leave. Maybe you're taking over from someone who's going on vacation. But you take over some code from someone. Maybe they're being promoted or what have you, and you have to understand how it works, right? And understanding how it works often means getting a really good understanding of how the implementation details fit together. You're not simply a user standing at a distance saying, well, just tell me what it does and that'll be enough. You're not dealing with code that's out there in some library. You don't even have access to its code base. All you have access to is the .jar file that's been provided to you. Instead, you need to maintain this code base, so you need to understand, you need to grok how it works. And when you have functional abstraction, there's often a lot of scattering of code in different places. So, you want to understand what's going on. You kind of see this, okay, this calls this and that. Okay, that's helpful. But what's going on there? What's going on this other place? And you got to sort of figure out, okay, how does that relate to the data structures being used? Where is this variable that's being used here previously set in a different function? And you got to trace back up through the calls. And at the start, the functional abstraction may help there, give you that high-level picture of what's going on. But at some point, you got to start burrowing down as to sort of where this thing that you're looking for lives. And that can be an issue with functional abstraction, that it's, now it's scattered in 10 different functions. And if you could somehow put it all together, then you could kind of see how the whole algorithm fits together. But now the algorithm is divided up into pieces. So this is an issue. It's an issue in often in certain circumstances. It's not a typical issue you as a user of the abstraction will face, as someone who needs a service from it, who calls it, but rather if you're going to maintain it. Have you folks encountered this before? Like you really want to understand what's going on, and you have the sense because it's distributed among 15 different functions. There's no there. It's like I look here, and yeah, that brings me to here, and it brings me to here, and it brings me to here, and you want to know. Okay, look, when the rubber meets the road, where are these things going on? Do you have that? Yeah. Okay. Now the other thing is performance. And I put in here modestly slower, and we're going to explore this issue. Under what conditions is it brutally slower? Under what conditions is it modest? Under what conditions is this performance associated with abstraction actually a gain? And to what degree is it a liability? I would say on a very often case, it's modestly slower. And we're going to explore this some. Okay. So let's talk about the performance implications. And in order to understand this, I'm going to draw on some of your knowledge from courses I think you've taken before. Undergrads here, have all of you taken 215? Is that, I think that's required as a course, is that right?
Yeah.
Okay, good. So we'll draw on that knowledge. And, it's interesting. You folks would probably find it interesting to see our faculty gatherings. You see all your faculty you see in different courses individually, and you start to see them interact. So you can see me interact with Professor Duchin or Professor Kuselik or whatever. It's an interesting mix of folks. But one of the things that we've been talking about recently is the fact that both because students choose their path through the program and because people forget. There's a lot of material in different courses, and people forget. There's certain important things that sometimes fall through the cracks by the time the student graduates in terms of their knowledge. They forget certain features because they only saw it in second year and they never saw it again. So one of the inspirations for elements of this course is to revisit material you saw earlier, but in a different perspective, in a different way, and loop around to it, link it in with other topics that may not have been linked to the first time. And that's done deliberately to sort of bring back this understanding and reinforce it, which we've decided as faculty is really important to make our graduates stronger in terms of certain mastery. Okay, so this is going to deal with 215 material, actually. How many people in here have taken or are taking a compiler-related course? Okay, power to you. Compilers, for a software engineer, for a practicing software engineer, compilers are one of the best case studies you can get exposed to for software engineering. They also unify elements of software engineering within issues of language hierarchies, what you can do with a parser compared to with regular expressions in a scanner. They help take a really big, nasty problem, divide it into bite-sized pieces, each of which can be dealt with different types of mechanisms, data structures, and they often involve, both theory and formal understanding together with really practical issues having to do with software engineering code structures and with architectures, with processors. So if you get a chance, if any of you have a chance to take a compiler course down the road, it's hard, but it's recommended. It'll be good for you. Okay. So here, we're going to be talking about some elements that also get into compiler issues, language engineering issues. Okay. So how does functional abstraction work? I mean, we've been describing it. Hey, let's go call up some code, right? So we don't. Okay, where's my Notepad++ when I need it? Okay, let's go back to Notepad++ here, and let's go call up some of the code. Okay, yeah. So here's some code we were looking at last time, preconditions, post-conditions. Here we have main. Main calls out to run scenario. Run scenario calls down to update space. Update space calls down to update cell. Update cell, in turn, calls off to this thing. What is this thing? We're going to come back. Okay, we're going to come back to this. What is this thing doing here? Anyone remember? It's a bit of a reminder of your C. What's going on here? What's this paren, star, end paren, and then a bunch of things after it? If we have this, what am I doing here? Well, so on.
It's a function pointer. You're giving a function as a parameter.
Right. This is a function pointer, and this is going to be important because I'm going to come back to this later. This is a function pointer here. Okay. We are in short passing down here, up here, function pointer. In fact, we pass down function pointers from further up. And why are we passing down those function pointers? A pointer to a function that does what? Well, it basically computes the liveness. This is how we determine, does this cell, based on its current situation, namely to wit, whether it's currently occupied and whether in the number of things around it that are occupied, is it live or dead in the next round? So it returns a Boolean. Is it live? Right? Probably could be named better. But it's a pointer to a function. There's some function that it points to, and maybe it's this. Maybe it's where are my functions? Maybe it's this compute liveness rand. Maybe it's compute liveness that takes into account if 1 through 3 cells around it will survive. Maybe it's this. If 2 or 2 to 4, maybe it's the classic rule for liveness. But that pointer to the function, it points to one of those guys, and we're going to call it here. So we have something like A calling B, and B calling C, and C calling D, and D calling E based on this pointer to the function. We don't even know for sure what it's going to call, right? It's going to call it based on pointer to a function. So we have this long, what we call a call chain. You heard that term before? Call chain? No? Okay. So maybe we'll make this specific just so we rather than abstracting it to a higher level and saying A calls B, B calls C, C calls D, I'll say main here calls off to what? Calls off to, well, in this case, I'll pay attention to run scenario. I'm not showing the complete call tree. Showing a call chain that can occur. Main can call run scenario. Run scenario calls update space. Yeah. And update space calls update cell. Yeah. And update cell calls off to this mystery function that computes some sort of rule. All right. So there's some sort of rule that it calls off to, which could be one function or another, right? So this is a call chain, and in fact, it's a dynamically determined call chain. Dynamic because we can't say ahead of time which particular rule will be called. We need to know what this is passing down to it, what's passing down from it. Does that make sense? And actually, later we'll see in this session probably, we'll see an example of main where that rule is actually determined by a command line argument. So we don't know till runtime, till we actually run this program with a specific command line argument. We don't know what it's going to call at that bottom call. Yeah, call chain. Okay, it's a chain. These are links in the chain. Okay, so it turns out that we're going to spend our time discussing call chains and specifically their runtime manifestations, their runtime sort of analogs, their runtime structures associated with them, okay? And these structures will differ from language to language. If you go to Haskell, or you go to Scala, or you go to Java, the details will differ a little bit, but the essentials remain the same. And we're going to come back to them. And understanding these essentials, ladies and gentlemen, will help you debug code. It'll help you, in some cases, understand why weird things are happening. And it will help us understand the performance issues, okay? And how to deal with them gracefully without twisting our code so that we have to bow to the compiler. or bow to the performance performance constraints by twisting our code, getting rid of abstractions. Okay. Okay. So understanding these structures will be valuable for you in terms of understanding trade-offs, in terms of figuring out how to deal things more effectively. Okay. So at runtime, so this is a call stack. I described main calls this, and it calls this, and that calls this, etc. Fair enough. What actually happens at runtime when it's actually running? Doesn't always make that sound. In fact, if it does, you get your computer checked, right? Ladies and gentlemen, what happens at runtime to support this? Well, there's this thing called a call stack. You folks remember that? Back when Dr. Eager was talking to you, did he teach you 215? Was it Dr. Eager? Yeah. There's a thing called the call stack, and the call stack is the basic mechanism used to determine to keep track of what's being called, what called me, so I can go back to it, and keep all the data in place. So suppose we had, a function called foo, and we call it with arguments 1 and 2. These are arguments for its so-called formal parameters. This is the declaration of foo. It has A and B in it, and it calls off in its body to bar. Calls off to bar with some expression of questionable significance. But it calls off to bar. So suppose we call foo. What's going to happen? Well, turns out what gets created here is something called a stack frame or activation record. It goes by 2 names. There's actually a space here where this information is stored. Now, you may ask, what this is actually in Java here. Well, we can adapt it to C in a minute. But what are A and B here? Why does it say A1, B2? What is that? What does that correspond to here? Why is A1 and B2? Where did that come from?
Parameters of the function.
Yeah, it's the parameters of foo, right? Called off to foo. A is 1 and B is 2. And it's got to store that information somewhere so that it can use it on an ongoing basis. It can say, hey, what is A? What is B, right? But also so that if it calls off to bar doesn't clobber these things. It doesn't overwrite them or make it forget about them, right? So whatever happens at bar, that shouldn't change the fact that A is 1 here and B is 2. So it actually saves these guys away in the stack frame. And when it calls off to bar, these things are safely stored away. It's like, you pack your items behind to go off on a trip. You leave your items behind your house. You go off and you come back and they're there, right? So we've called off to bar here. So foo is called bar. And that creates, that very call, each call creates one of these new stack frames. Where did the 6 come from? Well, that came from that expression of uncertain pedigree. And where did the C being 1 get called from? Well, it's B minus A, right? Okay, so foo calls bar. Are you comfortable with that? So we call off to foo, creates this stack frame, it calls off to bar, creates that stack frame, right? Okay, good. Now let's talk about a textured case. Okay, so you've seen this before, and you may be sick of this. You may say, I'm not going to go off into industry and use the factorial function. Well, yeah, but the point is it helps illustrate certain features which you do see in real programs. So suppose you have whoop, good shot there. Okay, so suppose we have fact and it takes in an integer n. What's the code for fact? Does anyone remember? We have an inductive case and we have a base case. What's the base case here? If n equals what?
1.
Good. 1. It could be, you could do it for 0. Would be another option, right? If n equals, I'll do it in the C style, although that's, as long as we're consistent, it doesn't matter. Okay, if n equals 1, what should I return? Sorry? We could return n. or we could return, to be clear, right? 1 factorial, remember that? 1 factorial equals 1. Good. Okay, good. So if it's 1, we just return 1. Else, what do we return?
Return is going to be n multiplied by factorial n minus 1.
Excellent, excellent. Who said that? It's Mahmoud. Okay, great, great. Right? This thing? Familiar with this? It ain't turtles all the way down, right? It has to stop here. So you start with n equals 5. You call this thing, and it says, I don't want to know, it goes here. And it says, okay, so I got 5 times fact applied to 4, right? And that calls and says, 1, no, okay, that's 4 times fact applied to 3. 3, okay, 3 times fact applied to 2. 2 times fact applied to 1. And that's what leads this, and then it wraps back up, right? And it returns the values successively. This is a beautiful thing. I wish I could discuss why. This is tail recursive. And actually, this can be turned in by a good compiler, ladies and gentlemen, into a loop automatically. Automatically. Well, semi-magically. It turns it into a loop. It can turn it into a loop, a good compiler. Ponder that for a minute. It actually gets rid of these stack frames. But in a naive way, it's going to create stack frames, okay? We'll come to optimization in a bit. So here we have these calls. N equals 5, 4, 3, 2, 1, right? These are successive stack frames or activation records. They go by both names, okay? So when we're calling this with fact of 5, these things are getting built up. And by built up, I mean they live in memory. They live in memory on your computer, and they live on the stack. There's this heap, and there's the stack. What lives in the heap? Can anyone tell me? What's living in the heap?
Dynamically allocated memory.
Yeah, dynamically allocated things. In C, it would be things allocated by things like what? Malloc and calloc. What lives in the stack? Well, things that are associated with local variables, parameters, other things created that are local to a given function, they live there. And it's important that they live there. It's important that each of these be created because fact is calling itself. I mean, you don't want a later call to stomp on what's been done in an earlier call. So, this guy has n equals 5. He has to remember that. That n is 5 here. So when he calls fact of 4 and gets back that number, right, that it can multiply by it. So he's going to call fact of 4, and fact of 4 is going to get back what, fact of 4 is 24, yeah? So he's going to get back 24, and he has to multiply it times 5, right? Yeah. He has to remember that n is 5. So each successive one has to remember their n, so when they get back the result of this, they can multiply by it, right? They can multiply their n by it. So they each have to remember it. Remember, did you see this at 215? Sort of? So, okay, well, I'm glad we're talking about this because it's going to come into play here in analyzing results, okay? So now you function call it. What's going to happen here? A is going to call, if A calls B. This could be fact calling itself. It could be foo calling bar. What's going to happen is it saves away for any information it has, like in processor registers. These really fast places we can look to store data. Did you talk about registers in 215? Yeah. Okay. These fast places. It doesn't have to get it from memory, and it just sort of holds it there. But if we're going to make a call, it needs to save that away in a safe place, like a place on the stack, on that activation record. It pushes the parameters for B onto the stack. Like each of these parameters here, it has to push them onto the stack here. So it's going to push them on there. And then it makes the call, including pushing the return address. And then it pushes a slot for any local variables in B. And then and sometimes it pushes all on other items. Okay, so ladies and gentlemen, what I'm trying to say is if we go back to our code here we go. we have main. Main calls run scenario calls update space calls update cell. What's happening when this is actually being called? Okay, we call main. Let's focus on this guy here. Calls run scenario here, and this passes here the count of iterations, and what's this compute liveness? What's this that's being passed?
Function here?
Josh, it's so we can read the data off of it. Yeah, okay. So this is the function to be used, right? Which rule is going to be used, right? And it's passing it to run scenario here because this is the work it needs to do its job. These are the two arguments, right? That it needs to do its job. So these guys get put on the stack so it can be passed to run scenario, and run scenario will then be able to do its job. And it calls off update space, and these things will be put on the stack and turn. The time and whatever was passed in for the rule, this rule. And in turn, this guy's going to call update cell repeatedly. It's going to call not just once, but many times. And each time it calls it, a bunch of other things have to be put onto the stack in theory, right? Right? Does that make sense? So there's a call, there's one of these. Can't point to it because it's here. There's one of these guys being created, one of these types of activation records with successive things here. The first one is main, and the second one is run scenario, and then update space, and then update cell. Those are being created here dynamically. And update space is calling update cell once with one for one cell, and then calling it again for another cell, and each time it's going back and forth, right? Boom, 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 just like that. In fact, ladies and gentlemen, you wouldn't believe it, but was I alive at that time? If so, I was very small, and I wasn't lecturing yet. There was a time where when you made this call, it would actually make a sound. It was called a thunk. Actually, I would have rather liked that, but these days our computers aren't quite as loud as that. But it was actually called a thunk, and it got a name, in fact, for certain data structures in compilers associated with these calls. Okay, so this guy is going to be building a call stack, right? Main, run scenario, update space, update cell, and it's going to be calling update cell again, popping back after it's done with that call, calling it again, popping back. And so the activation record is going to be boom, 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 like that. Does that make sense? Do you get what I'm saying here? Okay. Maybe you just don't know what to make of it. But the point is, it's calling the activation record as a dynamic thing. It grows and it shrinks as calls return. It shrinks. It pops things. After this call to bar here is finished, what happens? Should have emphasized this before. What happens after this call is done?
It's popped off.
It's popped off the stack. This goes away, and it's just back to here. Maybe this guy, well, he's not. He doesn't do it here, but he could if he called off to Baz, right? Then Baz would be put on here, and while that was going on, and then it would be popped off, right? So there's a lot of things going on in the stack, back and forth. A lot of action taking place because there's calls going on. So, getting around, what are the costs of functional abstraction? Well, one of the costs is you're maintaining these data structures called stack frames, or activation records. Now, you may think that this is all just pie in the sky theory. Actually, for some debugging sessions, you need to deal with these things, especially for languages like C and C++. I don't know the number of times I've had to look at activation records in C++ to debug some issue. So this is not airy-fairy stuff. This is like where the rubber meets the road for certain types of debugging. And if you want to be really skilled in understanding why your performance is lousy and how to improve it, this can be really useful too. And we're going to get to that soon. Okay. So one way to kind of understand what's going on and where the program is spending its time is what's called a profiler. And you'll find language after language offering profiling capabilities. What does a profiler do? Well, a profiler gives us understanding of the performance picture associated with a given program on, critically, a given set of arguments. So we call this program with these arguments, with these sort of parameters, as it were, provided to it. And it's going to go off and run its job, and we're going to get a picture of its performance at a couple different ways, often, sometimes many ways, using this tool called a profiler. So it's going to actually, while it's running, it's instrumented it to collect certain data from it while it's running, so that it can give us a picture about where it's spending its time, how much memory it's allocating, what types of memory it's allocating, etc. How many people in here used profilers before today's take-home exercise? Okay, couple. Common tools, and I realized they're probably not well featured in our undergraduate program, but they're really useful. They're really useful, and I'll generally use a profiler quite a few times a year, just to kind of give me a sense of where's this program spending time. Why is it so slow? It's often in response to that. Or why is it taking so much memory? The programs take a lot of memory. Why? It's not limited to C, but in C it's one of the easier languages to show it using GCC and gprof. Right? The GNU C compiler and the GNU profiler. And that's what I asked you to undergo. So we'll take a look at this. Far be it from you to think it's limited to C. Has anyone done profiling in Java before? There's a great Java profiler chips with the JDK, if I'm not mistaken, JVisual VM. And in contrast to gprof, it's a really visual thing. And it will show you where memory is being allocated, what type of memory it is, how much time is being spent here. It actually allows you to record the information in several different ways. It's like a point-and-click thing, really easy to use, and you can run it on your programs. And we'll probably come back to that in a few weeks' time with Java implementations of this. Okay, so profilers are good tools, and they can help you figure out what's going on here. Because you don't want to attribute it to X when it's really Y, and spend a lot of time investing in X, and it's not going to make a big difference. It ain't going to matter. So you want a profiler will help you put your efforts in terms of improving the speed into the things that matter, because it identifies the things that matter. And there's going to be some things that just don't matter. And ladies and gentlemen, let me tell you the secret. Let me come to the punchline. Probably in a given program, about 95% of it, 95% of it, it ain't going to matter. It's certain core aspects of a program, the critical path, as it were, although not in a project management sense. The core path that has to be tight. And the rest of it, to give an example, read state. Let's take our code here, just so I can emphasize this point here, right? Here's the code. Suppose I were to say, I am going to optimize the heck out of it. I'm going to spend a day making read state faster. How much do you think that will matter for the program speed?
Almost nothing.
Almost nothing, because look, it's reading it in up front. A very small fraction of the program time is being spent in read state, an extremely small amount. Where it really matters, where is this program's sort of core? Where would you guess that the sort of this critical path is, this core path that needs to be pretty fast? What's going to be hit again and again? What needs to be really quite fast for the program to compute quickly? Compute liveness. Oh boy, yeah. So Kyle's got it. Maybe update cell too, because these things are being called not once, like read state, not 3 times, but they're being called many, many, many times.
So 4 billion times.
Yes, something like that. That's right. So these things are being called many times, and so if you need something to operate quickly, you want to focus on the areas that are the bottlenecks, right? The rate limiting factors. And and a profiler will help us often identify those things. So let's go open up profiler results here. Okay, so no, I don't want to do that. Okay, so I should have this folder open. Pardon me for just a second while I go and open it up here. Okay, boom. And then we want this, and we want this. Yeah, here we go. Okay, so we are going to look at some profiler results, and we're going to start with which one here? Let's sort this by text so that we have all these together. Okay, and so I'm going to go look at this guy here, which basically is a version of the refactored. Well, okay, sorry for my discombobulation. Let's look first at the ugly thing. What do you think will be going on with the ugly one? Well, there's not a lot of action. It's all in one place, right? Let's go look at this ugly code just so we can remember what it looks like. Or is it burnt into your memory? Here's ugly, okay? Let's look at, do you want to look at ugly? Well, I won't ask you. Okay.
100.39% of the runtime.
Yeah, I know. There's some errors. We'll talk about that. It's not perfect. But basically all of the time is spent where? In main. Why is that?
Because there's nothing on
there ain't anything else. Well, that's not quite true. I mean, there's fget c and so on, printf, but really, it's going through and it's sampling this thing periodically is what it's going on. It's actually sampling where is it, and every time it looks, it finds it's in what? Main. Oh, it's in main. It's in main again. Main again. Okay. So it's recording this, and it's basically at random points it's grabbing. Hey, where am I? Main. Okay. So no surprise, main is taking all the time here. Okay. Now let's suppose we go to the next one, and we go look at outputs associated with the refactored solution. So here we have some information in two different tables. So you'll notice here that there's some indication of sort of the granularity. It's like a centisecond, right? 1/100th of a second, and it's seeing where it is, and then it's seeing sort of what calls what and how much time is being spent in a thing itself and in its children. So let's go through this, and there's some explanation here. Okay, so let's take a look at where it's spending the bulk of its time. Well, about 50% of its time is being spent in count surrounding live cells. You may remember that's called quite a bit, right? That's called here. Let me go back to it so we can just go see this. Okay, yeah, I have too many. Okay, too many of these guys open. Here we go. So update cell is being used here, and this is calling count surrounding live cells, right? Update cell is itself being called for every cell here, and it's calling off to count surrounding live cells, and count surrounding live cells is in fact, where is count surrounding live cells? That's, I thought it was further down here. Maybe it's much further than, here we are. So what is this doing? Well, it's going through all 8 cells, actually 9 once it just ignores the middle one, and it's counting the number that are live, right? So that's actually taking a very large fraction of the time. IsLegal coordinate is taking also about 20% of the time naively that it wakes up, or 19%. It's often isLegal coordinate. Index for row column. Do you remember what that was? Do you remember what index for row column was used to do?
Oh, because you're using a single dimensional array for the
Yeah.
two-dimensional model, and then it's just
That's right.
figuring out.
That's right. So index for row column, I had this very sweet little thing, if I may say so, where we look up in the current cells, and where do we look? What index do we look at? Well, we compute it here. This is instead of writing longhand, checking row times 100 plus this other thing, right? We instead have index for row column here, and we compute it. Now, that's hurting us. This call, which is occurring in the context of this thing, it's occurring many, many times, and it is actually taking up about 17% of the CPU time here, roughly. And then update cell about 9 to 10% of the time. Now these numbers are approximate. Why? Because it's based on sampling. It's based on periodically it samples, but it may miss things, right? It's doing every 0.01 seconds, so maybe it's doing it in a way that just happens to miss certain repeated calls, but it's probably pretty good in giving you a sense of what's going on. It's not missing any big issues in most cases, okay? Now you'll notice there's a distinction here between cumulative seconds spent and self seconds. Can anyone comment on that distinction?
Cumulative is what time the whole program is at, and the self-seconds is how long it's spent in itself.
That's right. So if we look at count surrounding cells, they're the same. Why is that?
Physics.
Why is it? What is it about count surrounding cells that makes those actually the same value there? What is it about this that means they're almost all the same? Well, it is calling off to index for row column and for is legal coordinate, but most of the time is actually spent. Okay, now this is interesting. I would have expected there to be a difference here. Is legal coordinate, by contrast, is this many cumulative seconds, and it is this many self seconds. By this function alone, it accounts for this, right? And this cumulative seconds is for this function plus the things above it in this. So the things that have called it. Okay, that's a bit confusing. It's not the things called by it, but the things that have called it. Running sum accounted by this thing. So in this case, we have index for row column. It's got about 2.08 seconds just due to it, but 10.6 cumulatively once we look up here. So once we consider that in is legal coordinate and count, it's taking this into account. So this is telling us basically of all the time, where is it broken down? We're successfully accounting for this about 12.21 seconds. Update cell gives us another clue where it's spending time, compute liveness. So we're getting diminishing returns, but this is taking quite a large fraction. This is successfully less. So it helps us understand where it's spending time. Now this is another way of sort of parsing it out by helping you to understand, for example, in main, it's itself taking almost no time in its body, but it's calling off to things which are taking a lot of time, right? There's 12.2 you'll recognize that. It's the same thing here. The cumulative, the total amount of time, the total pie that we're trying to figure out where it's divided. And not surprisingly, that time is spent in run scenario. If we look at run scenario here, a tiny bit of time is spent in it. After all, it's looping through for each successive time. But most of its time is being spent where? In update space, which is incidentally spending most of its time in this. So we could go to look at, for example, update space. And update space is spending most of its time calling off to other things, to wit, update cell and count surrounding live cells. Now, we could go into this more, and if you go look at the compilers or the profilers for Java, you can get even a richer picture of what's going on here. But it starts to give us a sense of where the critical path is, where the real bottlenecks are here. And as was stated earlier, I mean, if I go and I spend my time improving use clever strategies to kind of cut down the time in read state and write state, how much of a difference is that going to make? In this program, about zippo, right? For this program. If I went to sort of frob how I was treating command line arguments or textual encoding or whatever, very little gain. If I really want to make a difference, even update space, it's not going to pay a lot to invest time to get that optimized, by hand. But if I really want to improve performance, I should be concentrating on things where there's a large fraction of time being spent in them, like these top 4. That's pretty important. Those are ones that are being called repeatedly often, and a large amount of time is being spent in them. Do you appreciate what I'm saying here? So a profiler's output, beyond being just a description of where it's spending time, it gives us clues if we want to make the program faster. Where is it worth investing our time, and what things is it just AIGM? I think I introduced, certainly in 371, and maybe in this class, I've introduced this earlier acronym, YAGNI, the Agony Principle. Does anyone remember that?
You ain't gonna need it.
Yeah, ain't gonna need it. Don't over-engineer things. Don't spend a huge amount of time optimizing things you're not sure they're gonna be needed, or don't spend a lot of time putting in speculative features that might be needed by the client, by the stakeholder, when you're just guessing. That's one principle. The other principle which really matters here is it ain't gonna matter. It ain't gonna matter. There's a lot of times you put in some efforts, and if you're not careful and judicious about where to put in the efforts, you're going to spend a lot of time in things that don't pay off. And that's going to have an opportunity cost. Why do I say that? Because that time could have been spent on things that do matter. We could have put that effort into things that really do pay off. Does that make sense? Okay, so let's go and let's try to deal with this situation. But I asked you to do profiling. Did you get things like this roughly out? Okay, some differences here. Key thing, the idea was you compile it with a special option, minus PG for GCC. You run the program up front with arguments. And what is it doing during that run? It's very important to understand. What is it doing during that run? So we've compiled it with these special flags. What do you think is going on when you're running the resulting program?
The sampling you were talking about.
It's sampling and it's saving out the results to a file. It's actually saving them out secretly to a file. And then when you run gprof, it's reading that file in. Why do you have to provide to gprof? It's a bit confusing. The name of the program.
Can it profile multiple programs at once and like save all that data?
The main thing is that in order for gprof to get the names, for example, of this information, in order to understand the structure of the program, that information can be read from the program executable. And so it needs to know the program executable so it can suck in information about it. And it will suck it in, and then it will take that into account when doing this profile report. So it needs to know, not because it's running it then, the running's been done by that point, but it's because it needs to get information in it. Does that make sense? Okay, so it's sucking in this information and using this. Okay, but we didn't stop there, ladies and gentlemen. I asked you subsequently to go compile this program, to actually go time this program in its ugly state, the original ugly state. Ugly, but close to the metal, right? It's close to the metal. There's not a lot of functional abstraction going on. We've actually unrolled some loops, etc. We'll come back to discussing some of the optimizations. And we were running this program and observing the results in terms of time. And then I asked you to do it with not only the original program, the ugly one, but the abstracted one. And I asked you further to do it with some optimizations on at different levels, O2 and O3. So broadly, what did you find? Is there a difference between, if you don't have any optimizations going on in the compiler, is there a difference between the original ugly code and the refactored code?
Refactored code is
Much slower, right? I'll go and I'll show my results here. And unfortunately, for those on the web, oh man, I wish I could. I could do this here. Okay, yeah. So let me go save this, and then I'll just view it on my Windows side, so that I'm okay. Go get rid of that. Boom. So let's go exercise 3, and boom. Okay, here we go. Okay. So this is what I got out. Here's the ugly one. Here's the refactored one. And you take a look at this. Without optimization on at all, this hurts. Why is that? Why is that hurting so much? Think about what I said earlier about stack frames. Think about the work involved in a function call if done naively. What?
It's having to like modify and use stack frames repeatedly so many times that it slows it down.
That's right. That's right. So pushing on a stack frame. Think about that inner call, right? Calls to is legal coordinate, calls to count surrounding cells and so on. It's creating this big stack frame just to do that work and coming back. Think about index for row column, right? So this little calculation, it's calling off to this thing and creating a stack frame, doing a simple multiplication and add and coming back. And it's flapping, remarkably with abandon here between this guy and this guy. So we've multiplied the time by almost 7 times, right? 6 to 7 times here. It's quite heavy. 6 to 7 times slower. Now, I examined some additional alternatives, which I don't know that I asked you to require. I think maybe one, but not the other. So I had one with a cell rule abstraction. What's a cell rule abstraction? That's where this is a refactor where we didn't have flexibility. We just always yield the classic rule of Conway's life. Here we actually can use different rules down at the bottom here, depending on circumstance. And actually there's one which I created and which I'll put up on the site, where basically we use the command line argument to determine what rule to apply. So you say, hey, run it with classic, run it with an alternative rule like this or that or what have you. And it's a very simple thing. If we have time, we'll get to it today, otherwise next time. So ladies and gentlemen, those didn't seem to matter that much at this level. They didn't matter that much. I mean, basically there's stack frames being created in any one of these without optimization. Okay, then we turned optimization on at a more basic level than a more aggressive level. And what happened with O2? Did that make a difference in speed? Huge difference in speed. For which one? Well, for this guy here, the sort of close to the metal one, it made some difference by over a factor of 2, which is not trivial, but it isn't an order of magnitude, right? But for these other guys, it reduced it by like a factor of nearly 5 here, right? 52 to 11. And then I pulled out the stops and we did O3. And this is more optimizations. How did that make a difference?
It didn't make that much of a difference for the original ugly ones, but it was like a full order of magnitude for the other ones. Yeah,
a huge difference relative to the baseline, certainly, over an order of magnitude, right? And even compared to O2, a big difference, over a factor of 2, right? Almost 3. Mm-hmm. This difference here between O3 and O2, can anyone advance? I don't know if any of you looked into what O3 does compared to O2. But there's one big optimization that O3 does that O2 does not do. And anyone want to say what that is? That really accounts for probably a very large fraction of that difference.
Probably has to do with the stack.
It does.
Inline functions?
It inlines. It inlines functions, if possible, automatically. What do I mean by inlining? What do I mean by inlining? Let's make that concrete. So here I have my code, and I have. Let's go look at this. Go look at this code here, and let's go check out. Here this code for update cells. So here I call count surrounding live cells. I count index for row call, and I look up that information, and then I call this. So what is it going to do here for inlining? What do I mean by inline?
All of those functions that it would be calling, it just takes those functions and slaps it in that piece of code.
That's exactly right, Royce. So basically, ladies and gentlemen, it says, well, you may want to have a function named count surrounding live cells for your own use and for software engineering reasons, for clarity and so on. But as far as computation is concerned, I can take the body of that function and substitute it in here, as if it just you had that body, count surrounding live cells, and you had placed it, right into the text. So it's as if it does this, right? Goes and does this and puts it right up into here. Okay, here it is. It's as if it does this with the appropriate substitution of these values. I'm exaggerating a little bit, but it's as if this body is in there, and then count surrounding live cells equals count surrounding alive, right? Just substitute it in. So there's no stack frame being created there for each of these calls. How about index for row call? What happens there? What gets placed? It's even sort of more dramatic here. So index for row call. We'll go down and see where it's used. It's this guy here. So effectively, what happens when we are doing this? What does this essentially get replaced by for inlining?
That return statement.
Yeah, it just does this. It's as if the abstraction barrier doesn't exist at runtime. It substitutes that expression in. You don't have to see it, but that's what's going on with O3. It's actually substituting that in. So the overhead associated with this function call disappears.
So if we were to run a profiler on the O3, would it just tell us everything's a main?
So it's a good question. And my answer to that, Royce, is mumble. Because actually, I'm not positive how the optimization machinery interacts with profiling. And one of my concerns is that there's a bunch of profiling machinery that gets inserted, and I'm afraid the optimizer might tweak it and try to optimize it out, or and I'm not sure how reliable the optimization results would be. But let's put it this way, there's hardware profilers as well. I'm not sure how effective the profiler results would be. It might, and in many cases it will show the time. Well, suppose we had a hardware profiler. There are such things that actually in hardware sample.
Okay.
And what would that show? Almost everything in main, but that's what I'm getting to. What wouldn't be substituted in certain circumstances? What in this function would be amenable for this inlining, and what would be harder to inline? Harder. I'm not saying it's not going on. Actually, I think it is going on. Evidence would suggest it's likely going on here for most of those code bases. But what is hard to inline?
Pointer to the function.
Pointer to the function. It's got to be really clever to inline this, because it somehow has to know which one you want to call here, right? If it's calling off sometimes to A, sometimes to B, sometimes to C, you can't just always substitute A, right? That won't work. It's got to do something more clever than that. And it turns out that there are people out there in the world, and I used to be one of them, who day and night breathe compiler optimizations. That's what we did. That's what we do. That's sort of what we're thinking about. Not me so much these days, but I appreciate it, and I used to be part of that world, and it turns out people spend a huge amount of time trying to eke out these performance optimizations, and there's tremendous things you can do. And one of them, ladies and gentlemen, to compute this is to that would allow it, and I think it actually is substituting that. It's just collapsing lots of things. So remember, it's doing this inlining. So not only does that thing get cut, but that function we were just looking at gets put, its body gets put into the body of the thing that called it, and that body gets put into this. So essentially main, just like Roy said, is going to have tons of things inline. Main is going to go, it's going to become really big, just like what? Just like the original ugly code, just like this guy, but you don't have to look at it, right? Okay, so ladies and gentlemen, we're going to have here main, a whole bunch of stuff that's going to be inline into main. We're going to be inlining each of those things, so it's going to be, inlining these successive calls, and this call to this, to this, to this is going to lead to this. If it can determine this rule if it can determine which one, it's going to substitute into update cell. The body of that is going to be substituted into the update space, the body of that into run scenario, the body of that into main. So main's going to have all this logic in it, substituted, where possible. Now in this case, I think it is inlining that call to the pointer to the function. Why? Because it says, oh, you're always calling this with compute liveness, with this particular function. And it's doing what's called constant propagation. That's the name for it in compiler lingo, in optimization lingo. It's doing constant propagation. So when it substitutes successive bodies in, it says, oh, you're always calling this PFN compute liveness, is always compute liveness. So I can just substitute in the body for that. And it will substitute that in, even though it's a call to a pointer to a function. It will say, we don't need this pointer to a function to determine that. It's obvious it's this guy. And it will substitute the body in. So that seems to be what's in fact going on here. Now, in order to explore this more, I went and I did some experimentation. This was, memory serves me, this is a bit after midnight last night, if you're wondering why I look so tired. I was having fun. Okay. And so I went and I created a version of this code here, which I'm on exercise 2. Let's go to exercise 3. I created a version of this code where I was instead looking at, okay, let's sort it by that. So here we go. Cell rule abstraction, okay, and dynamically selected rule. Okay, so I created a version of this where the actual rule to be used is determined based on the arguments of the whole program. So the idea here is in main we have this call to determine the value of two command line arguments in as much as they affect the count iterations and the rule to use. And so this basically takes care of parsing command line arguments. It should really say determine, probably say read command line, determine arguments or determine values based on command line or something like that. Bad name. It was midnight. Okay, so what I did is I put in machinery for this, and I'm actually really unhappy with this machinery. This code looks god awful. It really troubles me. When I was in bed, I was like, oh man, that code is bad. Okay, so we've got to clean this up. But the basic deal is here, ladies and gentlemen, we parse the command line. If we have only one command line argument, we parse it as the iteration count. By contrast, if we have more than one, we first parse the command line argument for count iterations, and then we determine the rule here. Okay, excuse me. No, if we have just one, if we have no command line arguments given to us, in other words, argc is 1, then we just use the default iteration count. If there is one command line argument given, then argc is 2, and we get the count of iterations from that argument here, and then we we use the standard rule, the classic rule. By contrast, if we have two command line arguments given, we parse the second one to determine what rule to use. And this parsing, I would ask you to look at this, because I wrote this code first, and then I said, oh man, I would be unhappy if my students gave me this code. I mean, look at this. Look at this. I know you don't consider this bad, but this is not very modular. Okay, this is parsing the command line argument. Okay, if it's classic, then we'll use the rule for classic. If it's liveness 2 to 4, use the rule for 2 to 4. If it's liveness 1 to 3, use that. And I said, man, that's ugly. Why is that ugly? Why do I think that's ugly? I mean, it's the same basic logic, just written out longhand. I mean, it's not brutal, right? It's not hideous, but it's ugly. And suppose the number of possible rules grows to 100. Oh, come on. It was just horrible. I mean, you got to live with some dignity in life. So what I did is instead, I said, look, we can do better than that. I mean, this particular case, it's not terrible, but, I got to go to sleep. Got to sleep well at night and so on. So before I slept, I said, okay, I'm going to put in place a proper way to do it. And the proper way to do it is to have a table. Do it declaratively. For each argument, you have a corresponding pointer to a function, laid out, systematically. You go to 100, it's just a table. Or you read it in from a file or what have you. The point is, there's a nice way to capture this information rather than just longhand, compare this, compare that, compare this, compare that. That just goes on forever. You could just have a nice table, and then you have one nice thing that loops through these and tests if it's equal. Well, that is less bad, certainly. Okay, so I did that. And the point is, we're not determining this rule to use until what? Until we run the program, right? So the compiler's not going to be able to figure out ahead of time which rule to use in a clever way. Right? It's not going to be able to figure that out because you can't tell till runtime. It might determine which possible rules and optimize one for each of those. That is possible, but probably not. So let's go back to our thing. How did this affect things? Well, I added this right around midnight. Turns out it didn't really matter much in terms of cost. This cell rule abstraction and this guy, maybe they're a little bit more than this guy here, the refactored. I think here it fully inlines it. I thought it was inlining it here from something else, but maybe it doesn't. Maybe it gives up with the pointer to the function. But this one, where it determines it dynamically, there's no way it could be inlining it, and it's still got this call to the pointer to the function. But that doesn't hurt it too badly. So we still have this order of magnitude reduction in a big way between this and this, right? And now let's look at the ugly versus the refactored. You compare based on the first one with no optimizations, it's like night and day, right? We have paid through the nose for our abstractions. Once you consider the optimized versions, there's a cost. 2.7 to 4.1. There's a cost. It's no denying. I thought it would be on the order of maybe 20% or something, but no, it's actually more than that. But it's not even a binary order of magnitude. It's not a factor of 2, right? It's not a factor of 2 here. And even with the very flexible version where the rule isn't determined till runtime, it's not even, it's about a factor of 2 there between those. Now, suppose you would say, well, 2 is a lot. 2 is a lot. I don't want to pay for that 2. Well, first of all, ladies and gentlemen, optimization is going to be making much more of a difference. If you consider this and you consider what you gain via optimization, that's going to make much more of a difference than going from this guy here to this guy, for example. Going from this to this, saying we're going to cut out all abstractions and just have the raw code that we're going to put in place manually. It's not going to make as much difference as optimization will. The second thing is, ladies and gentlemen, optimization is, some optimizations can be done with a compiler, but compilers they're smart to a degree, But the real optimizations with programs, ladies and gentlemen, will often come by looking at the core algorithms, using a profiler to see where it's spending its time. This is a small toy program, but a much larger program, you're not sure where it's spending its time sometimes. And you'll use a profiler to figure out, and often it's core algorithms having to do with business logic. And sometimes it's other things like updating the screen or whatever. You want to put your effort into those things. And a compiler's not going to be able to do it. A compiler will take you down, for some basic optimization. It'll make a big difference. But to really get the best performance out, you're going to want to spend your time refactoring algorithms, changing it from an n squared to an n log n, or changing it from using, a lookup in an array or in a in a linear array compared to doing a hash table or something like that. By using the right data structures, by using the right algorithms, you're often going to be able to make a much bigger difference than you will see by removing lots of abstractions in your program. However, there is a case to be made, and I stand before you without blushing, case to be made in some cases about not putting in place abstractions. That case should be made on an informed basis based on profiler results as to where it's spending its time, understanding where the innermost loops of the program are, in other words, the real bottlenecks, and making a good judgment call. Does this thing need to be abstracted? Can we tell the compiler, for example, to just inline it? And will that help enough, or is it something that's not possible? There are cases where you will want to take those innermost loops and handle them differently in terms of abstraction, in terms of what you put into place than you will the body of the program. But don't let this difference here, 8 to 52, fool you into thinking that what you need to do is write everything in the ugly way, that what you need to do is forsake abstraction and just force upon yourself this sort of programming style. That's not going to help. And let me make one final point. If you do this, if you engage in this sort of program in this misbegotten sense that, it's going to help, first of all, you'll be leaving tons of money on the table, so to speak, in the sense that there's lots of things in here that don't have to be inline, like writing things out that you're manually in. I mean, what gain is there to that? 90% of this program, it's not going to make a whit of difference if you substitute the body and get rid of the abstraction. You see my point there? 90%, it's really that inner loop where it's at. And even there, ladies and gentlemen, often the time, if you do too much, remove too many abstractions, you'll be spending so much extra time debugging the program, trying to understand it, trying to test it, etc., trying to get it right for the first time. That time could have been spent on refining the algorithms that really matter, really reducing the computational complexity of the system, using better data structures. That's where the action's at. So to go back to that story of mine from a couple of times ago of that company, that was doing orbits for reserving plane reservations. That's why a very large fraction of their code could be in Lisp. It could be in a programming language that's known to be fairly slow. But only certain small portions of the program they would put into place in a language that was closer to the metal, because they could be mature in their judgment. Where does it matter, and where can we put the emphasis on abstraction? Where can we put the emphasis on making it really, really fast and tight code? So it's really about having a mature sense of that and having a informed judgment using tools like profilers and experimentation. And it's about realizing this opportunity cost. If you're spending your time maintaining your code base because it's so crufty that it takes a lot more time to debug, to test, etc., that's going to take away from time doing the most important optimizations, which are not the ones the compiler will do for you automatically, but the ones where you need to be really thoughtful, intelligent, and where high-level structure your program will help, not hurt that speed up. Okay? So that's all for today. I will be releasing, probably in the next day, the first assignment for this course. I will probably also have a little exercise for Tuesday at a take-home level. Okay? That's all for today. Thank you very much.